If x is greater than 0 and x times x plus 1 is 6, what is the value of x plus 1 times x plus 2? Okay, I think we can do this by inspection. So x times x plus 1 is 6. So I think 6 is 2 times 3. So there we go. So that means this is the 2, and the x plus 1 is the 3 because x is 2. So if x is 2, then that should be fairly easy to figure out, right? So that's going to be 2 plus 1 times 2 plus 2, and that is 3 times 4, and 3 times 4 is 12. What are all values of x for which x times the square root of 2 is equal to 2 times the square root of x? Okay, x times the square root of 2 is equal to 2 times the square root of x. Okay, so let's see here. What should I do? Square both sides. This seems like a logical thing. So x squared times, let's put the 2 out front, and this looks like 4 times x. Okay, let's put everything on one side, and let's see what else I can do. Let's factor out the 2. So that'll just give me x squared minus 2x. And then I can factor in x minus 2. And at that point, it's fairly obvious that x is either 0 or 2. So those are the values of x. Oranges are stacked in the shape of a complete pyramid. Each triangular-shaped layer has equal numbers of oranges on each side. A 4-layer display is shown. What is the total number of oranges needed to build an 11-layer complete pyramid? Note, in a complete pyramid, the interior is filled with as many oranges as possible. Well, this is 3D, right? Oh boy. Well, let's see here. We got layer. I'm trying to see if there's any pattern, because I obviously I just have this diagram. I don't have all the layers, so I've got to figure this out. So layer, and then what are we going to do? The number of oranges in each layer. So I think it starts off fairly easy, but then I'm going to have to figure this out. So we're trying to do 11 layers. So 3, 4, 5, 6, 7, 8, 9, 10, 11, and then I guess we have to total it all up. Yeah, we have to total. So total. So this is the answer here. Okay, here we go. So the first layer, that's fairly obvious that there's only going to be one orange. The second layer has 3, and you can kind of see that from the diagram, because you can see all 3. Okay, so the first 2 layers, not too much of a problem. Now the third layer, oh boy. So 1, 2, 3, 4, 5, 6. 6 is what you see, but let me think about this. Will there be 1, 2, 3, 4, 5, 6? Huh. So I have to figure out if there's an additional one in the middle for the third layer. And I don't think there is, so that means that would just be 6. The fourth layer, we can see it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there'll be one in the middle, so 10. So for example, if this is the fourth layer, 1, 2, 3, 4, 5, 6, 7, well, hold on, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's going to be one in the middle. So that's where you get the 10 from. Okay, and the fifth layer, you kind of go from there. Now, is there a pattern here? Well, I think I'm going to need to know one more. Let me do the fifth layer. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3. Okay. So in total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You know what? I just see it just from the drawing it. Yeah, just from drawing it. See, this is 1, this is 2, this is 3, this is 4, this is 5. So this is basically 1 plus 2 plus 3 plus 4 plus 5. That's how we get the 15. This one, this is 1, this is 2, this is 3, this is 4. So it's 1 plus 2 plus 3 plus 4. And that's 10. And this it was 1 plus 2 plus 3. This was just 1 plus 2. Okay, so I definitely got the pattern. This is just 1. Okay, so the next one would be 1 plus 2 plus 3 plus 4 plus 5 plus 6. You see the pattern there? That's 21. And then that's basically how you would get all the other layers without having to draw them out, which would be very time consuming. So this one you're going to add a 7, so that'll be 28. This one you're going to add a 8, so that'll be 36. This one you'll add a 9, so that'll be 45, correct? And this one you'll add a 10, 55, and then finally this one will add an 11, so 66. And then all of these, this is what should be added. I don't know why I put the box there, but this is what the total we want. When you add up these guys, all of these numbers, that's the total number of oranges in the entire complete 11-layer pyramid. And that number, well, I got to add it, is 286. A monoprime is a positive even number that isn't the product of two even numbers. An irregular number is an integer which can be written as a product of two possibly equal monoprimes in more than one way. What is the smallest irregular number? So let's talk first about the monoprimes as a positive. So 2, 4, 6, 8, 10, 12, 14, and so on, right? Because you're only dealing with the and so on. I'm not sure how far you want me to go here, or how far the question wants me to go, but let's just work with that for now. So we got the positive even numbers, at least the first few, and that isn't the product of two even numbers. That isn't. Okay, that isn't. So let me just see what is a product here. This 2 is 1 times 2. This is 2 times 2. This is 2 times 3. This is, well, it could be 2 times 4. This is 2 times 5, 2 times 6, 2 times 7, 2 times 8, and this is 2 times 9. Okay, so a monoprime isn't the product of two even numbers. So this is, so I guess that's not a monoprime. This is, so is that, so is that. So the monoprimes in this list are the 2, the 6, the 10, the 14, and the 18. Okay, and so on. Yeah. Okay, and then the next one is this irregular. Irregular number is an integer which can be written as a product of two monoprimes. Okay, so for example, 2 times 6, which is 12, that's the product of two monoprimes, this guy and this guy. That's just one example. So what do they want? Irregular number is an integer which can be written as a product of two possible in more than one way. This is the key right here. More than one way. Okay, I got it. All right, so let's see here. Well, if you take the 2 and the 18, that would give me 36. So the 36 is the irregular number, and these are the two monoprimes. But you can also get 36 if you do 6 times 6, because 6 is also a monoprime, and they have said that it could possibly be equal monoprimes. So there you go. That's what they're looking at. So what are they? The smallest irregular number is 36. So the key there is the smallest because there's going to be other examples, but all of those other examples are going to be larger than 36. So that's why they said smallest. The lengths of the sides of a triangle are 9, 12, and 15. A circle with its center on the shortest side of the triangle is tangent to the other sides of the triangle. What is the length of the radius of this circle? Okay, I think the diagram should be sufficient as is. I don't need to modify it. But I will draw one line to there, and that is the radius, and then this is also the radius from here to here. Okay. Now that triangle, they already told me it was a 9, 10, 12 triangle, so that means the base is a 9, but the base is not 2r. The 9 is not equal to 2r, because you notice there's a little bit of a extra there. Okay, so I'm going to use areas to figure this out. I think that should be fine. So if you look at the first triangle, so this triangle right here that I'm drawing in red, that triangle, and because that's tangent, that's a right angle, the area of that right triangle is 1/2 base times height, where the base is 15 and the height can be represented by r. And the area of the other triangle, I guess this one, can be represented by 1/2 base times height, where the base is r and the height is 12, because this is also a right angle, since that's the tangent point. They even use that word in there. Okay, that's the total area. So that's going to be 7.5r plus 6r, which is 13.5r. But we can also figure out the area of the entire triangle using 1/2 base times height, where 9 is the base and the height is 12. Correct? So that's going to be 54. So this is equal to that, because we figured out the area in two different ways, but they must be equal. So 13.5r is equal to 54, and when you solve for that, you get r equal to 4. If f at n is equal to the log of n over the log of 2006 n minus n squared, find the sums of all 2005 terms of the series f at 1, f at 2, all the way till f at 2005. Okay, so let's see here. First, I think I'm going to need to work with this guy here, so the base. So I have 2006 n minus n squared, right? Let's factor out that n, and then we'll get 2006 minus n. And then we'll use a log rule. You guys remember a log rule where if you have the log of a times b, that is equal to the log of a plus the log of b. So we use that. So this will be the log of n plus the log of 2006 minus n. Okay. I think that's pretty decent progress. And then what? And then I will go back to this original guy and see if there's anything I can do that makes it a little bit better. So if I have f at n, and then I have f at 2006 minus n, right? Here we have n, and we have this. Let's see what that is. So that would be using this function, the log of n over the log of, well, instead of writing that base, I'm going to write the base like this. The log of n plus the log of 2006 minus n. And then the log of 2006 minus n, this guy, will be the log of 2006 minus n over the log of 2006 minus n plus the log of 2006 minus 2006 minus n, like that. Okay, now let's clean that up. So that means this is going to be the log of n over the log of n plus the log of 2006 minus n. So nothing changed there. But this guy, let's see if anything changed. Log of 2006 minus n over the log of 2006 minus n plus the log of n. Okay, that looks very familiar. That looks very similar. So if I add them, the numerator becomes the log of n plus the log of 2006 minus n, and the denominator is also the log of n plus the log of 2006 minus n. So that means that's 1. That's a very, very good finding. This is 1. So that means if I take the function for n and then 2006 minus n and add them, it'll be 1. So what that means is that I can take this guy and pair them. So f at 1 plus f at 2005, pair them. Then f at 2 plus f at 2004. Got it? And then you kind of keep going like that, and eventually you're going to get to some of those values in the middle, which are f at 1002 plus f at 1004. And then the very last one, f at the one loner in the group that cannot be paired. Okay, that's pretty good progress. And then each of these guys, according to my calculations, is 1. So it'll be 1 plus 1 plus dot 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 plus 1. And then this guy, f at 1003, that I don't know. That I have to figure out. So that's going to be the log of 1003 over the log of 1003 plus the log of 2006 minus 1003. Okay. So a whole bunch of ones. Now, how many ones do we have? We had 2005 terms. The one I was not able to group. So there's 2004 that were involved in grouping, and I made pairs of them. So there's 1002 pairs, and each pair has a value of 1. So 1002 pairs, each had a value of 1. And then this guy looks to me like the log of 1003 over, this is 1003 also. So it'll be 2 times the log of 1003. So that looks like 1002 plus a half. So that is 1002.5. That is your final answer.